For decades, computers processed language with rigid, mechanical categorization. To a machine, a word is an empty container. It reads text by sorting discrete symbols into entirely separate bins, completely blind to the inherent qualities or definitions of the information it is organizing. The standard baseline for early natural language processing, including n-gram models and logistic regression, relied on a system called one-hot encoding. This graph illustrates one-hot encoding in action. Every word in the dictionary is assigned its own dedicated access. The word for car becomes a vector containing a single 1 and thousands of zeros, placing it at the coordinates 1, 0, 0. Its exact synonym, automobile, gets a different access, placing it at 0, 1, 0. When we try to measure the relationship between these two synonyms, we use a dot product. We multiply their corresponding coordinates and add them together. Because their ones do not overlap, the math yields an absolute 0. In linear algebra, a dot product of 0 dictates that the two vectors form an exact 90-degree angle. They are perfectly orthogonal. This creates a mathematical dead end. Because every unique word is assigned its own independent axis, a classical model perceives car and automobile as entirely unrelated islands. There is 0 structural overlap. In the 1950s, the linguist J.R. Firth proposed the distributional hypothesis, summarizing it with the maxim, "You shall know a word by the company it keeps." Instead of defining a word by a static dictionary entry, we can define it by its surrounding context. The first attempt to execute this theory in software was the word context matrix. An algorithm drags a sliding window across a massive body of text. Whenever a target word appears, the system tallies the adjacent words. Synonyms like car and automobile will rack up high counts next to the same contextual neighbors, like roads, driving, and gas. This technique converts human language into statistical behavior. Words with similar meanings generate similar rows of numbers. But this creates a defect, matrix sparsity. 99.99% of the resulting 10 billion cell matrix is filled with zeros. This sprawling, empty landscape consumes massive amounts of memory, and the data is far too scattered for machine learning algorithms to extract any underlying semantic patterns. To navigate a dense matrix effectively, the system requires a reliable mathematical ruler to measure the proximity between any two word vectors. Looking at this coordinate system, we run into the frequency trap. With a standard dot product, highly common words accumulate massive raw counts, their vectors stretching far into space. Multiplying any random word by and produces a massive positive number, tricking the computer. We fix this via length normalization. By dividing the raw dot product by the lengths of both vectors, we force every vector to shrink to exactly 1. They now rest perfectly on the surface of a unit sphere. This equation is known as cosine similarity. Because length is normalized out of the equation, the result is governed entirely by the geometric angle between the lines. An angle of 0 degrees yields a 1, indicating absolute contextual synonyms. An angle of 90 degrees yields 0, proving the words have 0 relation. By wrapping the vocabulary around a sphere, raw volume and frequency are rendered irrelevant. Semantic meaning is strictly dictated by the geometric angle between points. In 2013, Word2vec discarded the sparse counting matrix entirely. Instead of tallying occurrences, it uses a neural network to generate dense, continuous embeddings, compressing the entire vocabulary into vectors of just 300 dimensions. The algorithm responsible for this compression is called skipgram with negative sampling, or SGNS. SGNS bypasses the heavy processing of multi-class prediction. It takes completely unstructured text and formats it into a self-supervised binary classification problem. The model is not given definitions or grammar rules. Instead, it is forced to play a high-speed, relentless game of evaluating word pairs, guessing whether the pairing occurs naturally in text or if it was randomly fabricated. To see how SGNS generates its training data, look at this sample sentence. The algorithm places a sliding window over a target word in the center. In step 1, the window captures the actual surrounding context words. It pairs them with the target word and stamps the pair with a label 1. This tells the network this is a real linguistic relationship. In step 2, negative sampling kicks in. For every real word captured, the algorithm blindly pulls a set number of random noise words from the dictionary.
These garbage pairings are stamped with a label 0. To ensure the random sample actually selects useful, varied noise, the algorithm applies an exponent of 0.75 to the sampling distribution. This mathematical smoothing suppresses the dominance of ultra-common filler words and heavily boosts the probability of selecting rare words. Because the model is pulling blindly, it occasionally hits a false negative. It might accidentally pull a word that actually makes contextual sense and incorrectly penalize it with a label 0. The architecture relies on the law of large numbers to absorb this error. Across billions of sentences, a valid pair is labeled 1 tens of thousands of times. That overwhelming reinforcement easily washes out rare accidental 0 penalties. This engineered table of 1s and 0s builds a relentless environment of opposing constraints. The model is trapped in a geometric corner where it must systematically adjust the coordinates of every word to survive the classification game. The mechanism enforcing these rules is the binary cross-entropy loss function seen here. The blue term represents the penalty for missing a real context word, while the red term represents the penalty for failing to identify random noise. The gradient descent algorithm uses the positive terms to physically pull vectors closer together, increasing their dot product until the network correctly predicts their relationship. Simultaneously, the negative terms act as a repulsive force. Gradient descent violently pushes the unrelated label 0 vectors apart, driving their probability of being a match down to 0. This push and pull creates an emergent phenomenon known as shared contexts. Two words can end up physically grouped together in the coordinate space, even if they never appear in the exact same sentence. The vector for king is continuously pulled by context words like throne, rule, and castle. The vector for queen is independently pulled by those exact same contextual magnets. They become geometric neighbors because they share the same contextual friends. Semantic clusters don't mean the machine comprehends definitions. They are the strictly mechanical byproduct of vectors being dragged into position by shared contextual gravity. The algorithm has to compress hundreds of thousands of words into a strictly limited 300-dimensional space. To do this efficiently, it has to optimize the layout. Looking at this 3D map, the model optimizes its available dimensions by reserving specific trajectories to represent abstract human concepts. During training, replacing a male pronoun with a female pronoun requires a consistent shift in the surrounding contextual vocabulary. To account for this, gradient descent executes a uniform geometric translation, carving a distinct gender axis into the coordinate system. This creates the mechanics for vector arithmetic. If we isolate the exact trajectory of the gender axis and apply that physical translation to the coordinates for king, the resulting vector points precisely to the spatial coordinates for queen. Complex linguistic relationships, plurals, verb tenses, geography, reveal themselves as parallel parallelograms structured perfectly within multidimensional space. Because Word2vec relies entirely on historical data scraped from the internet, its geometric precision acts as a flawless mirror. It mathematically encodes human prejudice. In this scatter plot, we test the gender axis on professions. When we take the vector for computer programmer, subtract man, and add woman, the geometry points directly to words like homemaker and nurse. This is known as representational harm. When downstream AI models like automated resume screeners integrate these embeddings, they blindly enforce these geometric stereotypes against applicants. To counter this, modern systems require active debiasing. Engineers calculate the specific coordinates of biased axes and apply a geometric projection to orthogonalize them, flattening the prejudice out of the occupational vectors. Natural language processing evolved from plotting isolated islands to shaping dense, interconnected vector spaces. Rigid 1s and 0s were replaced by fluid spatial coordinates. The words inside the machine are never truly understood. They are mapped, pushed, and organized geographically through the brute force physics of gradient descent.